Okay, that's the last talk of the morning, by the way.
All right. So I'm going to talk about doing some gyrokinetic modeling of very basic turbulence experiments in LAPD. And this is sort of very different from most experimental work, and as you all probably know, I'm not an experimentalist. And it's the kind of thing, most experiments is people come up with a general idea of what they want to happen. They perform the experiment, something different happens, and then they have to try to explain it using theory. So this is actually motivated by theory. We actually want to understand how alphanic turbulence, how the nonlinear actions occur in alphanic turbulence. So we want as simple a system as possible, and we're going to try to essentially control the experiment and design the experiment specifically to answer very basic conceptual theoretical ideas about how alphanic turbulence works and how the nonlinear interactions work. So it really is kind of an experiment that's truly motivated by theory and a fundamental kind of theory, not just the idea that we want to achieve fusion or something like that. So it's a little bit different. Well, that's a nice theoretical idea. Let's have fusion, but you know. Yes. It is. All right. So I want to acknowledge my collaborators on this work. My postdoc Jason Tenbarge, and then Bill Dorland, Yusuke Numata, and Tomo Tatsuno, who have all been instrumental in improving and making AstroGK a useful code. And my graduate student who's in red, this is mostly actually his work, Kevin Nielsen. And also, of course, as always, the now defunct Center for Multiscale Plasma Dynamics.
I think we should consider it to be eternal.
Eternal, I say.
It's no longer defunct.
Yes.
It's just penniless.
No, I should put in memoriam, Center for Multiscale Plasma Dynamics. That's what we should do. Yeah. So everything will be dedicated to the CMPD.
No, I think the center exists. It just doesn't pay anybody anything.
That's true.
You know, in this country, we're familiar with this concept of an organization.
Right. So I'm going to talk about these basic turbulence experiments, a little bit of the theoretical background of the questions we're trying to answer, and then the experimental setup on the LAPD. And then really this talk is going to be focused most on the challenges for actually using gyrokinetics to model LAPD experiments. In particular, what we've done, validating that gyrokinetics is actually valid even at LAPD operating frequencies, which are typically a substantial fraction of the cyclotron frequency, which is typically a big red flag for gyrokinetics. And second, I'll show you some linear AstroGK results that actually reproduce what had been before somewhat unexplained behavior. Unexplained in the sense that we knew that it was sort of a moderate collisionality that was causing a difference from collisionless theory, but no theoretical treatments of it had been able to predict what the correct growth weights were. But the sort of full linearized, completely conservative Fokker-Planck collision operator that was worked on by Alex Jekochin and Ian Abel and Michael Barnes, that has actually resolved the problem, and it works beautifully in AstroGK. And I'll talk.
It was actually Ian who worked it out. I worked out that he should work it out.
Okay. Well, the man holding the whip should get credit. And then I'm going to talk a little bit about the next steps, the next things we're going to do, and then some conclusions. So to motivate this, first of all, we have the equations of incompressible MHD, which you're probably all familiar with. Now, as theorists, it's very nice to rewrite this set of equations in terms of Elsasser variables, where you add and subtract the fluid velocity and the magnetic field fluctuation. And essentially, Z plus is an Alfvén wave that's traveling down the mean magnetic field, and Z minus represents an Alfvén wave traveling up the mean magnetic field. And so these two equations combine into something nice and symmetric, this equation here. This equation has this linear term. So each of these waves is convecting along, or is traveling along the magnetic field line at the Alfvén velocity. I'm sorry, that should have been a vector. But and then there's this nonlinear term, and this is the thing we want to focus on. This is really where turbulence begins. This is the term that defines that there's turbulence. And typically, what we say is that this term is responsible for what we often loosely call collisions between oppositely propagating Alfvén waves, or Alfvén wave packets, perhaps. Now, when I'm saying collisions in this sense, I don't mean particle collisions. This is not the same thing when you're talking collision operator thing. It's totally different. This is sort of a loose use of the term that you've got two waves that run into each other and distort each other in some way. So they collide with each other in the sense of two cars running into each other and changing their shape.
But they very rarely pass through each other.
Yeah, that's true. That's true. They usually don't. But you know, sometimes people call this scattering, that the waves scatter off each other, and that's another term that's often used, and that prevents the confusion. But I'm just going to use the idea collisions, and that it really is in turbulence in Alfvén waves. And the other difference between a lot of the work we've talked about today so far in this is these are not drift waves. These are actually Alfvén waves. So we're talking about Alfvénic turbulence as opposed to drift wave turbulence. There are no gradients in this system, so there are no drift waves. To expand on this a little bit more, imagine that you have two Alfvén waves that are traveling along this magnetic field. So you've got the Z minus wave here and the Z plus wave here. Now, in order for them to interact nonlinearly, the other point is that if there's no wave going in the opposite direction, this nonlinear term is zero, which means that actually you can get exact solutions to incompressible MHD at finite amplitude. So there's no nonlinear evolution at all in incompressible MHD. It requires that Alfvén waves have to be going the other direction in order to have any nonlinearity. So if you want turbulence, you've got to have that. So in this case, you have that. And there's actually, if you think about this and look at the vector nature of this term, it also means that these counter-propagating Alfvén waves that you're looking at have to have some amount of polarization perpendicular to each other. I mean, they could be perfectly perpendicular, but there has to be some component that's perpendicular. That's the piece that's non-zero in this term. So this is sort of written, so this one has a bx as its fluctuation, and this one has a by, and they're both moving up and down the z-axis. So these counter-propagating Alfvén waves collide, and it's this nonlinear term, which is non-zero in this situation, that leads to transfer of the energy of those Alfvén waves to higher wave numbers. So they generate other modes nonlinearly. And as I said before, this is often described as scattering of the waves, because essentially what they mostly do is transport energy to higher k perp. And so it's sort of changing the angle of the wave vector, even though Alfvén waves are always actually moving along the magnetic field. So it's a little bit, that's why I don't like the term scattering personally. But anyway, so how are we going to do this in the LAPD? So it's quite I mean, of course, to actually do anything, you know, with complete control in an experiment is difficult. But we can actually do this in the LAPD, and there exist two antennas that are kind of ideal for doing this. The first one is what I'm calling here the C-loop antenna. It's Troy Carter's antenna. It's just this loop. You pass a current through it, and it gives you this.
C for Carter.
Huh? It is actually C for Carter. Yes. It was from a proposal. I just needed to make things clear, so I didn't have to keep like saying, you know, the loop antenna, this and that, whatever. So there was the C antenna and the KS antenna. This loop antenna that can give you a wave, and it can in fact give you a pretty whopping large wave, like, you know, 10% delta B amplitude, things like that. And then the other antenna is what I call the KS antenna by Craig Kletzing and Fred Skiff at the University of Iowa. They have developed this antenna over quite a few years. And what it has is it has 48 little grids that they can bias and drive independently, or, you know, in some arbitrary waveform. So you can create a wave that has any wave number within the range that you can do here, any wave number you want across this, and it gives you this beautiful wave that has no variation in Y. The antenna happened to be a little bit tilted in this experiment. This is real data. It was slightly tilted, which is why there's that sort of funny curve there with respect to the axes they have, and the curve has to do with just some of the data analysis. But the point is, it gives you no variation along Y, and you can control what the waveform is in X. You can specify a very precise Alfvén wave, and in fact, it's not actually an Alfvén wave, and I'll talk about that in a moment. It's actually going to be a kinetic Alfvén wave, or perhaps an inertial Alfvén wave. So one of the sort of kinetic versions, extensions of the Alfvén root, which are dispersive waves. So you can specify those, and we'll fire one down the LAPD, one up the LAPD. They can interact with each other, and then we can measure the nonlinear distorted KS wave, which is very precise with a probe, and try to determine what changes have occurred in that wave due to this nonlinear interaction. So,
why do you want to collide these highly different waves? Is this
well, it would be great if we had another one of these. That would be fantastic.
just
However, there
sort
are
of
two
setup
issues.
you happen to have?
Yeah, there's only one of these, first of all. And the second problem is that the amplitude of this antenna is not very big. You can't get a really large signal. So we know we're going to need to get as large a signal as we can in order to see the nonlinear interaction. This antenna can give you a whopping big wave.
So this means you can do imbalanced.
Well, I'll talk about that later. For those who don't know what imbalanced means, I'll bring that up a little later in the talk. It's kind of an unnecessary point at the moment, but yes, exactly. I mean, not only can we do imbalanced, we're kind of forced to do imbalanced. So that's the case. Now, if you want to know experimental parameters for the LAPD, this is the experimentalist version that actually has units. It's not a bunch of dimensionless numbers. So I have an almost equivalent one that's more of, well, it's a bit of a mix, but it's a little closer to the theorist side. So there are two regimes that are interesting to run the experiment in which we can do these kind of experiments. One is the kinetic Alfvén wave regime, and the other is the inertial Alfvén wave regime. And the way to distinguish between these two regimes, because a lot of people aren't familiar with inertial Alfvén waves, is it has to do with the ratio of the electron thermal velocity to the Alfvén velocity. So in the kinetic Alfvén wave, the electron thermal velocity is higher than the Alfvén velocity, and in the inertial Alfvén wave, it's lower. And what that means is, hopefully we're all reasonably familiar with the kinetic Alfvén wave. But the difference with the inertial Alfvén wave is that because the electrons are moving more slowly, it's the electron inertia that actually leads to the dispersive effect at small scales, which is why it's called inertial. And those are typically occur in the magnetosphere. There's frequently you have the right conditions to have inertial Alfvén waves in the magnetosphere, and space physics was one of the original missions of the LAPD, which is why it happens to be good at doing these. But for many other applications, kinetic Alfvén waves are more appropriate. And so, but we can do both of these in the LAPD. And gyrokinetics, fortunately, covers both of those limits just fine. Anyway, so a couple of things to note. In the kinetic Alfvén wave regime, the important scale, so the plasma dimension, I said 40 here, I guess 60 is probably a little bit better, whatever, I didn't want to change it. Anyway, 40, 60, whatever, that's the size of the plasma. The sound Larmor radius for these parameters is about 1 centimeter. So that's the scale at which things are going to be dispersive, roughly. In the inertial Alfvén wave, well, that's actually a much smaller scale because the electrons are kind of cold there, and it's actually the electron skin depth. That's the important scale that leads to the dispersive parameters. And they have slightly different behaviors, and we'll see what the linear dispersion relations of these two waves give you. Now, the other thing to note is the operating frequencies. So there, in these experiments, there were 70 and 130 kilohertz. The cyclotron frequency is only 223 kilohertz. This is for a singly ionized helium plasma. And in this case, it's 250 to 380, and the cyclotron frequency is 875. Now, as you're probably aware, gyrokinetics is applicable in the asymptotic limit that the frequencies of fluctuation are much smaller than the cyclotron frequency. So this certainly would give one pause as to whether you can actually use gyrokinetics to model the dynamics in LAPD. And we've taken very close look at that. As it fortunately turns out, you have to be actually very close to the cyclotron frequency, especially when you're at the small scales where K-perp rho s or K-perp rho I is of order 1 or higher. The cyclotron effects don't kick in until you're almost at, say, 90% of the cyclotron frequency. So so we can still say something. There is an effect, though, and we can see that effect when we actually look at the results here. And we try to take a lot of care in ensuring that we know that we're still in the regime of applicability of gyrokinetics. So that's the sort of the lead on to complications for doing this experimental program. Everything I talked about, the theoretical motivation of looking at these, was the incompressible MHD equations written in Alsacer form. But the LAPD plasma is not well described as an incompressible MHD plasma. It's just, that's a horrible description of it. And the reason why is, number one, and this is actually one of the most complicated things, is it's got moderate collisionality. The collision frequencies are of order the fluctuation frequency of the mode and of the modes. And what that means is that you have both a mix of collisionless effects, so you still get wave-particle interactions, Landau damping, things like that, but you also can get collisional damping. And that is notoriously difficult to handle analytically. And so that's why being able to use AstroGK with the advanced collision operator is really critical to be able to make this work. And so because of that, we really need to be using a kinetic description in order to do this, and one that includes a collision operator that's fully conservative. Other two things, finite Larmor radius effects, finite electron skin depth. We're interested in perpendicular scales that are of order the ion sound radius and the electron skin depth. So we're going to be looking at the kinetic and inertial regime. So this is certainly not incompressible MHD. These waves are going to be dispersive. And then finally, the finite frequency, which I've already talked about at length. Now, so the trick is we want to study nonlinear effects. But these properties above say that there's also going to be linear non-ideal MHD effects, the dispersive nature of these waves. So we need to be able to separate the non-ideal behavior from the nonlinear behavior if we want to correctly interpret the experimental results. So the beautiful thing is that AstroGK can model both the non-ideal effects, the fact that these waves are dispersive, including things like moderate collisionality, and the nonlinear effects, so that we can actually separate those and really understand what is just due to the dispersion of these waves versus what is really a nonlinear effect. Now, that caveat is that that's when the gyrokinetic limit is applicable, and we always have to keep that in mind and make sure that we don't violate that approximation. So the finite Larmor radius and finite electron skin depth are correctly modeled in gyrokinetics. You don't really have to worry about that. That's all included. To deal with the moderate collisionality, as I said, we're using this advanced and fully conservative collision operator, which has been developed, and there have been several publications about this, many of whom are authors sitting in this room. So anyway, but that has worked great, and I'll show you the results of that in this talk. The other factor is the finite frequency. Because the gyrokinetics excludes cyclotron frequency effects, we have to determine for each case what the magnitude of the effect of the cyclotron frequency is, of these finite frequency effects, and we'll see that in just a moment. And then another complication, of course, are geometry and boundary effects. I mean, the plasma is not infinite in size. Typically, we do flux tube calculations in a periodic box, so we're not directly trying to account for the boundary of the plasma or the geometry on sort of the size of the machine. It may be in the future that we'll actually tune some of the waves that we put into AstroGK to mimic, say, the loop antenna signal. The KS antenna gives you a nice clean signal that's easy to put in, but the loop antenna is going to be complicated. We may have to decompose that into its Fourier modes and then put each one of those into the code to make sure that we get something that's comparable. But that's future work. Right now, we're really just focused on the fundamentals of how does one well-defined wave interact with another one from the theory and numerical side. So we want to validate that gyrokinetics is actually applicable in an LAPD plasma. So we want to ensure that the finite frequency effects, which are excluded from the gyrokinetic description, are not too significant, that they don't cause a problem. So we can do that quite easily using linear theory. So what this plot is this is now for the parameters for the kinetic Alfvén wave regime. I have a number of things plotted here. The first is an analytic gyrokinetic solution of the dispersion relation. So what the frequencies and damping rates should be based on linear collisionless gyrokinetic theory. And that's this short dashed line that goes here. Then I also have plotted the Vlasov-Maxwell solutions for the two operating frequencies that so there are some experiments that we're going to be modeling. Those are the operating frequencies that they've actually used. So you can actually see the cyclotron effect here. I mean, it does have an effect, and the frequency here, the biggest differences in the frequency, in the damping rate, it's not really that big of a deal. But in the frequency, depending on which one of these operating frequencies you're using, which is either 30 or 57% of the cyclotron frequency, you're off by maybe from 5% to 20%. At large K perp, or sorry, at small, that should be small, ignore that. At small K perp rho s. But the nice thing is that as you go to higher and higher K perp rho s, those differences become smaller. And that's because the cyclotron resonance effectively doesn't start to have an effect until you get to much closer to the cyclotron frequency when K perp rho s is a larger value. And you'll see that in all of the plots. So this is the way that we can say, well, how valid is this? Oh, and then of course, these are the linear results from AstroGK. So we're able to reproduce the frequency and damping rate quite well using linear calculations. These are all collisionless, all of these determinations here. So adding the collisions is something we can really only do numerically, and I'll show you that in comparison to the data in a moment. So this is the case we find. So we have to be a little careful about our interpretation of measurements down here, because we think this should be the wave frequency, but if you're operating at 0.57 omega I, the measured frequencies will really be down here. So we just always have to keep that in mind and know what's going on there. Now we can do the same thing for the inertial Alfvén wave regime. Again, the effects are sort of less than 10% here, and they decrease at higher K. There's bigger effects in the damping rate down here. However, one thing to note is this is a logarithmic scale, and pretty much anything below about 10 to the minus 2 won't make any difference in the lab whatsoever. It's effectively undamped. So whether we're off by a factor of 10 or 100 here doesn't really make any difference to actually trying to model the experiments, which is a fortunate thing. Now this is the more of the theorist view of what the or what the LAPD parameters are. It's exactly the same parameters: magnetic field, ion electron temperature, electron density. It's just written in mostly the dimensionless quantities that theorists think about. So we're dealing with plasmas that are either betas of 10 to the minus 4 for the kinetic Alfvén wave regime, or 6 times 10 to the minus 6 for the inertial Alfvén wave regime. Anyway, so this is the set of parameters we have. So now we can go ahead and compare to some actual experiments. So the tricky one that they were having problems predicting by theory correctly was the inertial Alfvén wave regime. So what we have here, the crosses are actual LAPD data. These were taken by Craig Kletzing, Fred Skiff, and a graduate student named Derek Tex. So they took these a couple of years ago at LAPD and wrote a very nice paper about this. But what we see is that these are the collisionless results, both gyrokinetic and for the Vlasov-Maxwell case for the operating parameters at which these data were taken. So you can see that the frequency is predicted to do that and decrease. This is characteristic of the inertial Alfvén wave. It's dispersive and it leads to slower velocities. But the data clearly do not follow that collisionless path. So, and the reason why is because of the moderate collisionality of the LAPD plasma. And where the difference is really striking is in the damping rate. The damping rate, now notice this is a linear scale, because in the lab, we're not sensitive to the many logarithmic orders of magnitude that we can deal with theory. All we're sensitive is sort of what we could actually measure in the time and length scales that we can do in the plasma. So this is plotted in that sense. So the collisionless damping is anticipated to be almost 0 right up to K per d delta E of 1, and just increasing a little bit. But the measured damping rates in the plasma were an order of magnitude or more larger. So there's a significant effect due to the collisionality in the plasma. This is the kind of thing that if you want to model this correctly, you really have to get these collisional effects correct. And that's difficult. Fluid methods are unlikely to be successful at doing this properly. And even kinetic methods, you have to have a collision operator that is conservative in number, momentum, and energy as well in order to get these right. If you turn some of those properties off, it completely screws it up and you don't get the right answers. Well, depends. It depends on exactly which one. It generally screws it up, I'll say that. So, so the point is, and people had done, actually, when this data was first published, they did some simple theories, collision operators that were variously conservative. But they could never get both the kinetic and inertial Alfvén wave regime results correct using a single model. They just couldn't do it. And so we were fortunately able to do it. So what I've shown here are Astro GK results using this collision frequency. And so what we see is that these triangles do in fact follow through the data quite well. Now, if you take Brzezinski and you say, well, let's estimate what the electron collision frequency is based on the plasma properties as far as we know them in the plasma, it gives you a collision frequency of 7 times 10 to the minus 6 inverse seconds. And so we found that the best fit of this data to Astro GK was a collision frequency of 1.2 times 10 to the 7 inverse seconds. So that's pretty darn close. A factor of 2 on the kind of thing we're dealing with, that's agreement in our book, I think. Huh? Well, it's not quite 2, but it's, 1.4 to 1.2.
Yeah, that's true.
Right?
Well,
You verified that the collision, the neutral collisions are.
We have not. We have not. I mean, the code is fully ionized, so there's no third neutral species to have an effect. The fact that with a realistic value of the collision frequency, and mind you, the parameters in here aren't always all that well known, and they may vary across the plasma and everything else. So this number, I mean, you have to take with some. I mean, I don't have any error estimate on it, but there clearly is an error estimate there.
well,
So.
there's also the collision operator, of course, is only meant to be quantitatively correct up to correct with a unity, so it's
Yeah.
perfectly fine to have a prefactor. It would be an interesting question whether that prefactor depends on anything. But presumably you're about to answer that question.
No, not really. I mean, this is just one. I mean, this is the one constant that goes into the model. Of course, there's some velocity dependence and so forth in the operator.
If you simulate, if you do another LAPD run with different parameters, will you have to fit again? Or can you just use that proportionality?
Well, the actual collisionality in the other regime changed because the plasma parameters changed.
What I'm saying is that I understand, but
Yeah.
the proportionality constant between Brzezinski and Astro GK.
Oh no, it's different. That's in my opinion within the error of doing all of this. You'll see in a moment. It actually fits really well there.
So for any given case, you will have to have a different fit.
Right. I mean, the basic idea is what we would do for a given set of parameters. We would do some runs so that we could determine what the collisionality is. I mean, both using Brzezinski from the plasma parameters and using linear Astro GK results. Then do our nonlinear results where we use the same collisionality, and then we can determine what the damping rates are going to be.
Suppose you
Yeah.
have a smaller collision frequency in Astro GK code, so make the new EI. How does the result look like?
Okay, hold on. Let me go to the next slide. So, this isn't changed very much. This isn't half. But what I show here is for this case, so we at the higher frequency, where actually the cyclotron effects are a little bit larger. Again, the real big difference effect here is not the cyclotron effects of sort of 10% here. It's the fact that you're off by an order of magnitude in the damping rate. Now, why is this important? It's important for these nonlinear or for these turbulence experiments because you're sending in 2 low K modes and you're deriving nonlinearly some energy into higher K modes. If you don't know what the damping rate of those higher K modes is, you don't know whether you're going to see anything or not. You want to be able to predict, we need this amplitude of our initial waves in order to actually see a measurable signal. And this is going to have a big effect. If your nonlinearly generated wave is at K per dE of 1, it's going to be strongly damped. And if you're using collisionless theory, you're going to get the answer completely wrong. So that's why it's important. So anyway, but what I have here is 2 different values of the collisionality. So you can see how it varies the results of the damping rate here, and the same thing down here. So it doesn't change the linear frequencies all that much, but the damping rate changes a bit. So you can kind of see it certainly is tunable. And if you turn this down by a factor of 10, you'll be way off. So it is reasonably well constrained. I mean, this is sort of plus or minus 20% or something like that. So and again, it's compared to that value, and I think that's a pretty good result. We get even, I think, better results in the, there's one other thing. So another thing you can do, and I'm not going to claim that this is necessarily a good thing to do, but if you wanted to say, well, of course, there's also this 10% difference here, and if you want to do a little bit better than that, you could cheat a little bit and say, well, we know what the difference between the gyrokinetic and cyclotron frequencies are due to the linear modes. And you could subtract that off and see what the fit is of these modes with it. So if you focus on this here, when I sort of subtract the difference between this gyrokinetic prediction and the cyclotron prediction, it brings those points right down into agreement with the experimental measurements. So, of course, the cyclotron frequencies have an effect, but we think that it's not going to be, detrimental to understanding the experiment. So that's before the correction, and that's after the correction. So it gives you a pretty good, way to compare exactly if you want. I won't necessarily say that that's necessarily a good thing to do, because cyclotron effects could have other effects and it might change the nonlinear dynamics, but just at least in this linear case, it gives you something nice. Now, in the kinetic Alfvén wave regime, interestingly, the results they got were not very dependent on, they looked like they were consistent with collisionless conditions, that they didn't need a collision frequency. And when they tried to fit it with a sort of simplified models of collisions, they got way off. They couldn't reproduce this result. And I think it's because their collision operators never conserved momentum. And so it was the conservation of momentum that was critical to actually get this right. So as we turn up the collision frequency, again, we have collisionless results here, and then with a little bit of collisions, and it doesn't change the answer very much. And that's for the Brzezinski collisions are supposed to be 1.4 times 10 to the 6th inverse seconds. We're using a value of 1.2 times 10 to the 6th. And we get results that are pretty consistent with the measurements. And so we're pretty happy with that, because when they tried to do it, as I said, with the analytical models, they just got way off if they tried to include collisions.
So you're saying the important thing about using this collision operator is that only using correct collision operator produces a situation where collisions do not have an effect.
In the kinetic Alfvén wave regime, exactly. And it's because they conserve momentum. Yeah. And if you try collision operators without the momentum conservation, you get the answer wrong. So it damps much more, and you see a big effect in this regime. So again, this we take as evidence that AstroGK is doing a really good job, and that the collision operator, this is effectively a real experimental validation of the collision operator that they developed. So again, this is for the higher operating frequency, and again we see results that are in agreement with that same collision frequency.
Is LAPD fully ionized?
No, well, it's not, but it doesn't seem like the results make a difference. It's certainly possible there's an effect, but our fully ionized numerical simulations seem to be reproducing the behavior. So it may be that it's a fairly small effect. Pardon me? Well, as I said, we're able to reproduce all of the damping with a reasonable collision frequency without considering the neutrals. So,
what's the collision rate?
they
neutrals in these conditions?
Well, they don't really know what the neutral. There's not a good handle on what that is experimentally. They can't measure it very well, which is another reason why I can't really model it, because we don't even know what the measurement is.
Calculated it in LAPD for the
Yeah.
we're using. We can help you do that.
Yeah. Okay.
Is it large or small compared to
In the regimes we were looking at, it wasn't big. But
Well-
I don't know about these parameters.
Yeah.
And you're right, there is some uncertainty in some of the cross sections involved, but it's not that uncertain.
Yeah.
But these are electron collision frequencies, so these are probably bigger than the ion neutral frequencies, or even electron neutral.
Yeah, well, we can calculate it. Yeah.
I'm wondering whether the reason this works is this a coincidence, or does it work because the collisions with neutrals actually are subatomic? There's a trivial way of showing that.
Yeah. Or down by a mass ratio, or a root of a mass ratio, or something.
You'll find it to be small.
Yeah. Anyway, we didn't study that, but we seem to still get results that are good. So the suggestion there is that it's not having a significant effect on the results. But as I said, we did not check that. We don't know for sure. So for current and future work that we actually plan on doing at some point, the next thing that my graduate student is working on right now is trying to determine what the nonlinear energy transfer rate dependence on amplitude is. So these waves, and I'm going to expand on that statement in a few moments. So the energy transfer rate is going to depend on the amplitude of the waves. Well, certainly the amplitude of the counterpropagating wave. And so we need to be able to do that so we can determine what are the amplitudes that you need to have in the experiment in order to actually see a measurable signal, a measurable nonlinear signal. So the idea is that we can actually guide the experiment and tell them, look, these are the operating parameters you need to be in by doing numerical simulations rather than just having them tune a bunch of parameters until they see something. So hopefully that saves on runtime. The second thing is, we can also try to predict what the nonlinear product we should even be looking for is, and then make direct comparisons to what we actually see in the experiment. A third thing, which is a little bit of a side note, but I'm going to show a little bit of result from this because it's kind of cool. So based on the idea of Alsacer variables, I said, well, look, why can't we just measure both the E and B and add and subtract them in the appropriate way so that we can separate out a wave that's going up the field from a wave that's going down the field. This is important because one of the waves is going to be large amplitude and one is going to be small amplitude. So you don't want to wash out the signal you're looking for by this large amplitude wave that's passing by. So is there a way of sort of using what we know about the linear characteristics of these wave modes in order to separate out those signals? And the results are pretty good. So I'll show you that just in the end. So to expand a little bit on the amplitude dependence.
Sorry, could I just ask in connection with all these projects? So, but what about the geometry? Is it important that...
Well, that's kind of a even further down the line situation. I guess I could have added that as another bullet.
Now you're modeling LAPD as a periodic parallelepiped, right?
Yeah. Well, the important effect, if we really want to compare, like, directly experimental results to our calculations, would be to model the C-loop antenna's waveform correctly, because that's not a simple, plain wave. It's well, most of these measurements are taken in the inner sort of 20 or 30 centimeters, so it's really in that center where it's pretty uniform. And if our wave, if our antenna and our wave is actually larger than that, they don't see a lot of end effects. So you just stay in the middle of the plasma.
So why are these guys so concerned about modeling it correctly? They have a Brzezinski curve. Pavel is doing this complicated job of geometry.
Because they care about fusion, not fundamental physics.
And the difference between fusion and fundamental physics
is about 100 years, probably.
Well, but they're trying to model all these wave interactions correctly, right? Is it, well, if I took, and Pavel's paper said that it kind of works, right, or something like that. So if I took bound or bound plus and ran it in a box like that, would it still work?
I'm not as familiar with the
Is Troy listening to this?
Yeah.
He was earlier.
The phone rings
Call him
again.
now.
Oh, it's now like 4 a.m. and he's already been up till 1, so I think he's...
Alex, aren't they worried about flows and stuff and shearing near the edge?
Well, that's sort of what I'm asking, should Greg be worried about these things?
Well, the point is we're not in the edge, we're nowhere near the edge, and we're trying to stay away from the edge because we're trying to do as simple a calculation as possible. So
but is it, because they have bound, right? Simply one could actually add on to this question, whether the geometry is important. Because it looked to me, when Troy shows his alphane waves, right, they always have it's always these sort of circular blobs.
Well, that's because it's his loop antenna, which produces those things, and they tend to rotate.
The boundaries don't matter.
Pardon me?
The boundaries don't matter.
I think I won't say they don't matter. I think they're a higher order effect, and in the region that we are, I think that we can at least, on first take, we can ignore that.
Well, that's good. Even in fusion, I think if they did it in a periodic cube, they wouldn't have any confinement problems.
Right, yeah. All right, so I just wanted to briefly mention, so this idea of the amplitude dependence, as I said, we're going to be colliding a plus and a minus wave. Now, if we consider just the evolution of this minus wave here, it's determined by this equation, which has several terms in it. There's, of course, this linear term, so this wave is just moving along at the alphane velocity along the mean field. And then there's this nonlinear term. And so if you look closely at it, the nonlinear term, it's this operator, z plus dot del, operating on z minus. So this thing is the operator. So that's the thing that leads to the nonlinear term. So it depends only on the amplitude of the oppositely propagating wave. So our nonlinear energy transfer rate is going to depend on how large that amplitude is, which is the reason why we need to try to crank up at least one of the wave amplitudes as much as possible. We'd love to do both, but our like really highly well-defined waveform antenna just can't get really high amplitudes. But the other one can. And so what we're going to do is then send a very large wave. Sorry, this is sort of backwards. I mean, consider the antennas on the other side. But send a really large wave to distort this small wave and measure the nonlinear interaction and distortion of that small wave. That's effectively what we want to do. Well, I know, like I said, the antennas are flipped. So the loop antenna would be over here and the KS antenna would be over here in this. I was tired. It was 3 a.m. last night when I was doing this because I couldn't sleep because jet lag's been killing me. So the point is you need to ensure that you have sufficiently fast nonlinear transfer over the time scale of the experiment so that you can see the mode that's produced. Otherwise, you're just going to be stabbing in the dark to see if you see something, and that's probably not a very efficient way to go. So the whole point of this is that we should be able to do pretty darn detailed numerical experiments to tell us what we need to do in the actual physical experiment.
So are you focusing now on the long wavelength regime? Is that what you're doing here?
Well, I don't know exactly. I mean, we're probably we'll drive them at sort of 0.2 or 0.4 kperp rho s, our initial waves, and then look for something that's around.
Because if you look at the full equations,
Yeah.
not just the Alfvén regime,
Yeah.
are there other nonlinearities?
Yeah, but I mean the dominant nonlinearity is very similar. I mean this is the whole point, is that the kinetic approach, gyrokinetics, is going to include all of that. Whereas, otherwise we would just use an incompressible MHD, but we'd get the problem completely wrong and only be able to do sort of a really hand-waving comparison.
Yeah, I just have never looked at this problem of the nonlinear behavior when you're actually in either the kinetic Alfvén wave or this inertial regime. And I just wondered whether you still have the same basic nonlinearity dominating.
It's not exactly the same, but it's I think generally it's the same, and it does have this property that these waves are still cascaded by the oppositely propagating wave. Mostly, co-propagating ones can interact, and whether that's important. Pardon me?
There's no self-steepening of a wave.
Not that I know of, no.
Well, kinetic Alfvén will interact with itself.
Interact with itself, or
Well,
Well,
with
so
another
it's
one,
self-steepen or
with another one going the same direction, exactly. But we're not going to put those in. So, but yeah, no, I don't think that they evolve. I don't know for sure. I mean, this is actually a very good question that is something I'd love to do in a PIC code, is actually determine whether linear kinetic Alfvén waves are stable and at what point they go unstable as you crank up the amplitude.
No, I don't think it's about self-steepening as much as about whether you still have kinetic Alfvén waves, you still have plus and minus waves.
Yeah.
But the waves of the same sign can interact with each other because they disperse and they can catch up with each
Well,
other.
that's what I was wondering.
Right. So the
Yeah.
only way to make them not interact is if you're launching a wave
same
packet
K-perp.
that has an exact, which is on a ring in K-perp, which you have a bunch of
Yeah.
waves, all of which have the same K-perp.
So they have the same propagation
In which case
group
the whole
velocity,
thing
and
is
so they won't
because-
interact with
because
each
the
other.
Special relation is K-parallel V
Yeah.
times K-perp rho I. Right. So if they all have, if they only vary by K-parallel, but have the same K-perp, then they won't be. Then they will not be able to interact with each other.
Yeah. No, these are good questions, Jim. I mean, they're things that we don't necessarily know the answers to, and it's part of the reason to do all of this, to try to nail down. I mean, part of it, some of those questions we can answer just with the numerical simulations, if we believe them, of course. But then this is actually to verify that it really works that way in the real world.
Well, so in the numerical simulation, you could, or in LAPD for that matter, you could try to launch a wave, a bunch of waves with just one antenna.
Yeah, but they'd be in the same polarization. They wouldn't interact, and so
Would they not
it's.
interact?
Well, you wouldn't be able to like switch. I don't. Well, I don't know. Possibly, but that's not the first set of experiments we're going to do. So it may be possible, but there are experimental constraints that are beyond a theorist's understanding, apparently. So.
No. I think there are theoretical constraints which experimentalists should
Yes, yes, okay.
Before turning, before pushing the on button.
Anyway, but the point is that it's not completely known. And I mean, that's part of the whole point of this entire research project, is to understand it. I mean, I've only been presenting it in this incompressible MHD way because it's simple and it's easy to explain. There's obviously a lot more complication, especially in this dispersive wave regime. And so, that's exactly the kind of thing we want to explore. But I don't want to go into crazy amounts of details about that. So last brief thing I want to mention, because I think this is kind of cool, is so if you just stick your probe in the plasma and measure as a wave goes by, this is just one wave, it's launched from one end of the plasma and then it bounces off the cathode and it comes back. Okay? If you measure E and B doing that, you get signals that look like this, green and blue, and you're like, yeah, okay, what's going on there? You can't really tell which wave is going one way, which wave is going the other way. But you can, and so you can't distinguish those. But what you can do is if you add them in the Cell-Sasser way. Now what I'm not showing you is that in fact these are kinetic Alfvén waves and this relation doesn't exactly hold for kinetic Alfvén waves. There are some other factors in here, betas and various things. But if you put those in, and you can sort of figure out what those are from theory, if you put those in correctly and you do this sort of L-Sasser adding and subtracting, and the fluid velocity is just the E cross B velocity, so you get it from E, which is measured. You can do that, and when you do that, you can see the downward, the wave that you first initially launched there, and then the reflected wave comes out here. Now you may notice that this isn't exactly perfect, but in fact, Fred Skift, who did this work, actually discovered that he did a little simulation of it and realized that is actually a real effect, and it's actually giving you what's there. There really is some other bit of downward propagating wave at that point, and that's beyond. I don't even know the details of that calculation, so I won't present it. Z plus and Z minus, but they're sort of corrected for being dispersive waves.
Well, if it's dispersive, doesn't it make sense that the poles would spread out?
Well, it's just a single wave mode, though. So they're not exciting a range of wave modes. I mean, there's going to be some range just because it's not infinite, but that's not the point. I mean, the amplitude difference is just because it is being damped and it's bounced off the cathode, and so there are some funny things that go on. But the whole point here is that you can actually separate upward and downward going waves. And this is just with one component of E and one component of B, but we're now building a 2-component E, 2-component B probe that's going to be able to give you all the in-plane electric and magnetic fields, and you should be able to completely decompose your waves. And you have to do this by wave vector too. You can't do it, in MHD, it's all wave vectors are the same because they're non-dispersive, but in kinetic Alfvén waves, you got to first Fourier transform and then do this adding and subtracting, and then you should be able to separate the up and downward going waves. So this is just something that we need to do that we hope is going to help experimentally in measuring what we want to measure. Pardon me?
Is it linear?
Yeah, I mean, the determining, because this isn't exactly right for kinetic Alfvén waves, determining what you have to add to what is something you can determine linearly.
Did you add finite causality?
No, we haven't done that. So, and that may have an effect. So we don't even know if this will exactly work, but it's just kind of a cool, new idea that's sort of a theory-inspired bit of experimental diagnostic. So anyway, in conclusion, LAPD experiments in simple geometries can use to test fundamental concepts of plasma turbulence. And these basic concepts in their most simple form are based on MHD theory, but lab plasmas aren't really very well described by MHD. So we can apply gyrokinetics, a much more physically comprehensive model, to model these experiments. We can model both linear non-ideal and nonlinear effects, at least as long as the gyrokinetic approximation applies. We can handle moderate collisionality, which is often a very big challenge, by using the advanced collision operator we have. And we really have to keep a close eye on finite frequency effects to make sure that we account for those. And finally, we've actually been able to successfully model both kinetic and inertial Alfvén waves in the LAPD. And the next thing we're going to do, as I said, is perform nonlinear simulations to both guide the design of the experiments and interpret their results. Thank you.